Okay, so welcome everyone. Let's see, we have kind of a three-part plan agenda for today. First of all, apologies for last week. We had a mess up on scheduling and didn't get the invite out. So we kind of used the session, didn't record this session. Instead, we kind of spent some time planning. And one of the things that spent out of that was this background project we're going to start working on. So I'll announce that as kind of the third part. So the three parts of the agenda tonight would be one, just finish up the notebook that we had on rotary positional embedding. Two, there was a couple of papers that were referenced in there. We're going to just do a real cursory coverage of those papers. So that was the linear biases and extending context windows through positional interpolation. And then lastly, we'll talk about this background project, the very small language model project, and just get some initial brainstorming, at least orientation on that. Okay, so let me start, I think, this guy.
Do we have any new folks on here? Actually, sorry, just before we dig in. Anybody new that wants to say hi? Yay, nay. Okay, cool. Go ahead, Roger.
Okay, so just a really quick background. The idea with rotary positional, is it embeddings, is this idea that instead of adding some sort of, in the original attention is all you need paper, they added positional encoding information to the tokens right after the embedding layer. And then that was used by the attentions layers above that. Instead, rotary position does two things. One, instead of adding something, it uses a rotation and consequently preserving the magnitude of the vectors. So it's kind of like taking your vocabulary and rotating it through this large high dimensional hyperspace. The rotation is an increment for each position in the sequence. And so the embedding for dog, if this was dog at one position or the beginning position, for the second position, that embedding would be rotated through some angle theta, and out at the fifth position, it'd be rotated through 5 thetas. And there's a kind of a sequence of those. It's pairs of, let me call them frequencies, rate of rotation on each of 2 dimensions, 2 dimensions, 2 dimensions, et cetera, through all the dimensions. So that's what the rotary position embedding is.
Hey, Roger, quick question.
Yeah.
So you mentioned 5. Is that because there are 5 words till you get to the original one dog?
Yeah, well, so this would be like if you just embedded dog at position, let's say 0. Then this is representing obviously in 2D, not a high dimensional, but
sure,
that represents dog. And so if dog was that, so kind of that point, it's showing as an arrow, but it'd be that point in the hyperspace. If you had dog and you added positional embedding to it, quote unquote added, then the new coordinate for that would be rotated through some angle theta. And then if it was at position, I don't know why these are going backwards. It should have been, it starts at, it would have been these must be 3 different examples of dog. One is a sentence that's just dog, one is a sentence that's the dog, and the other one is the pig chased the dog. So in this case, dog is at position 5, so it would have had the embedding, quote unquote, added to the dog token embedding, which would have rotated at this 5 theta.
Okay.
And is the idea that if it was the next word, it would go even further?
Yeah, it'd go another theta more. And theta is a constant here, but it's actually, well, it is. I guess it is. It's a constant. They actually add in all the dimensions. So like the first 2 dimensions are the theta is very large, so it moves fast. The next one is smaller, so it moves slower, et cetera, through all the dimensions.
Okay. So you get about 18 thetas in this case. You get about 18 words before you're wrapping around. Wait, it's about 24, I meant.
Yeah, but it wraps around in one dimension, but meanwhile, the next two dimensions would have
Yeah.
rotated a little. So by the time you wrap around, you're really not the same theta because the theta for the lowest two dimensions is wrapped around, but the theta for the next two dimensions has just started.
Oh, okay.
Yeah.
Like,
Yeah, that's the problem with this two-dimensional depiction, I guess, of it, right? Instead of n-dimensional.
Yeah, exactly. It's hard to show,
Yeah.
right?
Yeah.
Okay, so anyhow, I'm not going to go through the whole RoPE paper. I just wanted to give a quick kind of review of it, just to orient. What we had done is gone through the paper, and then we had gone through this notebook that I had created, which was really just kind of exploring ideas around RoPE. In part two, we covered most of that. This is just coming back. And I'm going to touch on a little thing here that Julia suggested, and then we'll finish up on here, last couple of concepts on here. One thing I did want to mention here, because I didn't get this right when I first read through the paper, RoPE also differs from the original Attention is All You Need paper in that the positional encoding in the attention paper is added to the token after embedding. Sort of add into the embedding. I mistakenly thought that rotational embedding was also occurring here, but that's not the case. That rotational embedding actually occurs inside of here on the query keys and values. It doesn't occur in the residual stream of the transformer. So that was interesting. That was Ted pointed that out during, I think, part one.
so it happens on the other side of the skip connection. We don't see a skip connection here. But if
Yeah, you don't because it's going through this add norm. I think that got changed.
Oh, that's-
I don't think I have an example where it shows it as a residual stream. But Ted has a good presentation where I think this guy got moved because, like you said, the residual stream should go all the way.
Mhm.
It just skips around each one's, which if you can redraw it, I'll try adding that to maybe to the notes of YouTube. But there is a representation where you see the residual stream and you see the embedding flowing all the way from the bottom up to the output token, next token prediction, with attention adding to it and MLPs adding to it, etc.
Okay, yeah, if there weren't the residual connection, then the skip connection, then you could say it's just an optimization because if you rotated before the projections, then you would be doing an unnecessary thing. You can go ahead and combine that with the projections and just get it down to one matrix. But I guess that maybe that's not true because you're learning those. You're not learning okay, never mind.
Yeah, I'm not sure the overall impact of moving it out. One of the things is that, so in one of the papers I read, it showed the value. When I looked at, I think it was Hugging Face implementation of RoFormer, they included the positional embedding for the value as well as the key and query. But in the original paper, I think it just talked about key and query. So I'm not sure if that's true. They were talking explicitly about keeping it out of the residual stream. I can see some places where it might be advantageous. You know, if you go find one token and you now know something about where it's located, you can make a query reference to where it's located to find something close to it, or something like that. So, but it's different than what I expected anyhow. I was going off this drawing. It's not the same as this. There afterwards. I don't know if I don't think I have a picture that shows where it's added into the heads, but it basically each of the query key value heads have it added, multiplied. Okay, so that was the paper part. We came back and we had started with this this notebook, and again, I won't go through it, all of it, although I think I wanted to cover, where was it? This one? This is where we explored, yeah, here's Julius's thing. So I'll do this section real quick. This is where we explored creating weight matrices that rotate. So the idea here, I was thinking that was that you would take an unrotated a matrix, or actually a residual stream that had rotation in it, and you would add some amount of rotation to reference back to some prior token. But let's see, so I went through and explored just taking a matrix, having weight matrices that rotate it, then did the rotation of the embeddings and multiplied the weight matrices times those hidden states, the X's, with the embedding already added. So again, this was more thinking of it like that original attention is all you need. Then we were looking at if you query 10 times key 0, you get a smaller value. If you take query 10 at position 10 times a key at position 10, then you get a full match. So that's kind of what we were looking for. And then taking a query at 10 and rotating it backwards 10 steps, you could see that basically that means that, let's see, query at 10 rotated back at 10 times the key at 0 is a match. So you're taking a query at location 10, you're saying, let me rotate it back 10 and then see what it matches. And if you attend to the original key at location 0, then that's a strong match. And it's no longer as strong of a match at the current. So it just shows that you can rotate the query, I guess it'd be query vectors. You can rotate the query vectors to make them attend to prior times. I want to skip forward a little bit here. This was, so along those lines then, Julius, I don't know if you remember, but you kind of said, yeah, well, not only can you rotate those queries, you could add a few of them together and get kind of a combined query. And so I just did a quick test of that as well. So here's a query that rotates back 5. Here is, a key at 105, a query at 110, and we will take the 110 rotated generated query that rotates back 5 from 110. So that's this guy. What's this one? This is a query that's rotated back from 110, rotated 10 back from 110. And now what I'll do is I'll create a combined query that is the sum of those two. And then in this particular case, I don't know if you need to do this. There might be advantage to not normalizing it, but I normalized that combined query. And then took the combined query and tested it against the keys at 100, 105, and 110. And we could see we got pretty good matches at both 105 and 110, as we would expect. So that's, Julius, your additive or adding queries together to be able to do a query on both points. Does that make sense?
That can be learned.
Any questions anywhere? Yeah, that's right. You could learn a query. And I think we explored that last time, didn't we? I think we made it through here where we looked at creating queries. If you ignored some of the higher frequency components, the lower dimensions, you could make queries that were very broad. So the blue is a query with all the rotation position bits or dimensions. And these other two colors are the ones that are either a query rotated, a query dropping out the first few n dimensions, setting them to 0, or you could also do it in the key when you're embedding it. So that made it broader. And I think we did here. So this was additive also. Then this is where you're just adding two of them full dimension. So one at minus 2500, one at minus 2100. And when you multiply that times the input sequence, you can get a match. So let's see, plot reference would be a query that matches just at one location, and the orange is matching at 2 locations. So same type of thing. You could learn how to build a query that would be much more broader. What is this one? Oh, I think I just did. Here's this orange now is the match with a combination of adding multiple locations, multiple queries, but also getting rid of the early dimensions that makes it much smoother, much broader. So the attention here is the match that you get with this general smooth query. And I just did another example where I was trying to shape it a little bit more, not get rid of as many points, I think. So kind
Hey,
of,
Roger.
yeah.
Roger, I don't know if it's going to be a repeat of what you have already covered in the previous meetups. I have not followed up on the YouTube channel yet. So when you say minus 2500, that's the sequence going back 2500 words. Is that what it means?
Yeah, so
Okay, not the degree or angle or anything. It's just
no,
the
it's positions. It's just
positions.
positions. Yeah,
Okay,
yeah.
and then sometimes you
I'll post I'll add it back to Slack, but I posted this notebook. And in the very beginning, you can look at, this implements the rotary position embedding. So it's got its sines and cosines and et cetera. And then we also implement, where is RoPE? Oh, RoPE is an implementation that does the compute optimized. So you basically, instead of doing an n by n square matrix with elements along the diagonals, you just do two of them with the two matrix multiplies, basically adding the sine and cosine. So you can look at that if you're interested in that. I'm sorry, what was the rest?
right, and the second question was where you mentioned about dropping the dimensions. So this is assuming your token or query or key in a head is, let's say, 128 dimensions. So you are zeroing out some dimensions. Is that what you're doing, or is it?
Yeah, so right. So let's see, there was a picture. Yeah, this picture shows kind of how the sines and cosines work with rotary embedding. So in the very low dimensions, so this is dimension index along the bottom, and this is sequence position along the left-hand side. So I mean, there's too much change here, so the pixels get aliased, but basically the lowest dimensions are changing very rapidly. And as you get further and further higher dimensions, they change less frequently. So the last one is not changing at all during that. So that's the computation. I think Ted had posted a picture similar to this when we were in the part one, but this was just a recreation of it. So that kind of the intuition is, so you know your position based on these values, right? But these are the ones that change fast. So it kind of feels like those are going to be the fine granularity, high resolution information. And these out here are going to be much lower resolution. So if we have a query that's looking for a specific location, what if we take the query vector and hide the position information that's this high frequency stuff? Could we then get a query that was less selective and more broad? Does that make sense?
Yes. So yes.
Okay.
And also, how does that account for proximity? I guess in some sense it also accounts for the proximity. Maybe the dimensions, as you go higher in dimensions, those pertain to more broader information versus the dimensions which are lower pertain to
So
more temporal
yeah, so the
information.
proximity, we can take this rotation matrix that you can generate and rotate values to be able to search at a particular point. So if you rotate it the equivalent of 2,500 positions, then when you query against the key at the last rotated back 2,500, you'll get a query that'll match that same key, because these are being dotted against, it should be dotted against the same unit vector. So the sequence that you're looking at is all the same. So all the keys and all the queries should be identical, except that you're adding position information, embedding in each of the end locations. So when we try to say, I want to match a key that matches the position, my key at location at the end of this window, minus 2,500 positions, that's why it's matching back here. So this is the query that I'm being generated. I rotate it back from its current position back 2,500 position. It'll match a key that was at this position.
Right, right.
Does that answer the question?
That's for the position, and maybe I kind of mix the two position and the dimension in terms of the frequency of the changes, right? So the other diagram that you have.
So that's where we did the this one. I'm adding several queries together using Julius's theorem, and then here's where we're saying take the first 250 dimensions, zero those out on the query. So it can't tell high resolution information. It can only tell this broader resolution, and that's when you get a match against your data. Again, where the data you're matching against is the same key over and over and over, but rotated a different amount. So it's kind of showing you how that key would match at any one of these locations.
Right. And do you know why you have these little spikes at 750 and 4,250?
No idea. No, I don't. No, so that's the reference one. Shows up here as well. I never asked that question. Shows up in all of them. I guess it's just, if you look at this recreated, I think one of those pictures in the paper, the product isn't unity at all. I think it shows some of the sine cosine stuff coming through because it's the addition of a bunch of sines and cosines at different phases. And so somehow that's inducing that little notch. I don't know the answer to that question.
And may I ask one more question?
Sure.
So if you go back just slightly, yeah, right, this one. So if I look at, let's say, point 2, then there are multiple positions where there is intersection of your query. So how do we disambiguate the position in this case?
So just make sure you understand what's being drawn here. So this is a query. First of all, you have one random vector, and you're copying it through the whole sequence. So it's a sequence of that same vector, and then we add in the rotation embedding into that. So they're all position embedded. And then we take the last token and rotate it back 2,500 to be the query. So that would be essentially a query that should match the one at 2,500 since it's a 5,000 long sequence. Because the key and the query are identical. The query's been rotated back 2,500. And then we just plot the similarity, the dot product of the query and all the positions with the embedding added to it. That's what this is doing. The other two lines are the same thing except zeroing out on the query some positions in the query. That is probably, this one is 350. So that'll be the orange one. We zeroed out part of the query and now the match is smoothed out. And then also show that if we zero out the data, oh no, on this one, sorry, I'm not zeroing out the data. I'm just doing a broader, larger zeroing out of the query, 350 dimensions in this case, 260 in this case. And then this is how those queries match this sequence of data X with embedding positions embedding at each of those positions. So this crossover isn't that's not positional information. This is the degree of similarity between a query and a key that are identically matched except for the position embedding that's been applied to them.
Yes, and I don't want to take too much of everybody's time. I just probably what I wanted to ask was, let's say if I look at this cross section, right, then I have multiple places where the same key matches against multiple queries, right? So that's where I was going.
No, it's one query. It's one query against a sequence of keys that have their position embedding applied.
I see. So it's matching multiple of those, and it just happens to be that way.
This is, yeah. This is what the match would be at that location. I'm just plotting the dot product of the query and the sequence.
Okay.
Okay.
Yep.
I'm going to roll on. Okay. This one I am going to skip because that didn't work. Okay. What did I do here? I was wanting, that's also, I'm going to skip. Additive embedding, I think I don't recall if we did this, but I wanted to look at the it originally proposed in positional embedding, which is an additive, it adds sines and cosines. So here, instead of multiplying it, we just add the position embedding. It's the same sine, cosine at various frequencies that rotary position uses, but instead of multiplying it in complex plane, we use it, we just added it in. And they didn't talk about a scaling. Last time when we were talking through this, I added the scaling just to show kind of, otherwise it was dominated by the position embedding. Here I wanted at least to have some of the semantic embedding added in as well. And I plotted that then. So this is a query using the additive. This is a query against the same type of stream, unit vector stream, using the additive position embedding. And we get something kind of similar-ish. And when I went through, actually, this is it slightly different where it's centered on the match instead of having the match. Here the match is out in the middle. Here I think this matched the paper where they have the match starting at 0. So I did that and I ran it several times. It actually was pretty stable looking for that. And I started wondering, so what was wrong with the additive position embedding? Because it seemed to work, and it worked even at a non-zero location. I could shift it out. You're still getting a pretty good similarity match, a pretty good kind of selective decaying attention type of thing. So the next thing I explored is that if I take and have an offset, so I've got two position embeddings, and I take the norm of those two. So this would be the equivalent of like 10 positions away. Well, okay, 10 positions away. What's the norm of the difference between those two positions? And it came out to be a number, and the number was very constant through time. And it was independent of the offset. So it kind of had this nature of no matter where you're at, the norm of the difference between the position embeddings that you're adding is going to be the same. And I think that was the original hope, was that you'd be able to, because the original paper talked about being able to support relative offsets. And I think this was probably what they were picking up on. But the problem was, then I said, okay, that's cool. Let's try, how do I form a query that's going to query back 10 positions? And that's where the problem came in, because then my natural instinct would be, okay, just take the difference between two embedding positions at one location and apply that to another location. But it turns out that here I'm plotting not the norm of the difference, but actually the difference. So norm of the differences in the embedding. What is this? So this is the difference. This is kind of my approach at look 10 positions back. And then I was looking at the norm. If I use that same bias that same offset all the way across, what does it look like in terms of the norm of the difference? And you can see that it's not constant at all. So it's not easy, whereas it's easy for rotation to learn, like, how do I rotate back 10 positions? This looks like a much more complicated, whatever, if there is a transformation, it's much more complicated trying to figure out how do I make a query that at all positions looks back 10 positions. So I think this is probably why the rotation was better than the additive. Okay, I'm going to skip along. Real quick, because this is a little bit off topic on it, I also realized that we were looking at, I was looking at the dot products before the softmax, but actually in attention you have a softmax afterwards. So I wanted to see, so what does the softmax look like? And this is, the only thing you really get out of this is, I did it initially, I was getting weird values because I expected the softmax to make, like, select the peak attention, the most similar one, and amplify that and push everybody else down. That's kind of what my understanding of softmax, the role of softmax. And when I did it, I found that, so if this is two numbers, these are would be the logits, these are the logits normalized, and this was my softmax. So actually the ratio between my logics was much better before the softmax than after the softmax. And that kind of threw me for a loop. I didn't understand why that. I thought maybe this from scratch implementation of softmax might have been the problem. So I compared it to the torch softmax, and it's the same. So it wasn't a equation problem. And so what I found is that when I do this with larger numbers, 2 and 6, as opposed to if the logits are 2 and 6 instead of 0.2 and 0.6, now I see that gets amplified significantly in both my implementation and the torch implementation. So it was the magnitude of the logits that was making it sharper. And if it's less than a certain value, then the attention is squashed. If it's above a certain value, it gets amplified, kind of the winner takes all type of theory. And I just didn't have that intuition before that. I haven't gone back and looked where they put the batch norm layers, but it seems like it's important then the scale, the sum of the logits, that magnitude is important, because if it's too low, then you're not gonna get a winner takes all. So it needs to be above some value. Okay, so this was just, here's some raw logits. The other part was, hey, this can be done with temperature. The way that temperature, I went back and modified, this doesn't have temperature, but the way temperature fits into the equation is like this. So you divide by the temperature. So you can essentially scale up or scale down those logits based on temperature with respect to the softmax. So raw logits, without changing the temperature, you get something like this, which is about the same-ish, maybe a little squashed, it looks like. But if you apply a temperature in here, here I scaled the logits and I get a really high winner takes all. And here I did the same thing using temperature instead of scaling the logits. So anyhow, that's a little, again, this isn't RoPE, but a little intuition about softmax. Any questions or anything on that? And then I just completed it and did RoPE with softmax included. So this is the logics before the softmax. This is the logics after the softmax at a temperature of 0.2. So it, depending on the temperature, can make it very selective. I don't actually know in typical transformers what temperature is set to. Or is it 1? Does anybody know? Is it 1 maybe, and you learn
They had 1. Since they divided by the square root of the model dimension, they were sort of using that as the temperature. So they probably,
that's, sorry, Julius. Yeah, that's what it is. Go ahead.
yeah. Yeah, has anybody ever learned the temperature? It seems like that should be a learned parameter.
I think the defaults for transformers is 1, yeah.
Yeah, they're sort of giving it to you. They're saying we like square root of model dimension as the temperature.
So one of the reasons for that, if I understand, is of course, the variance needs to be contained, but that needs to be contained a lot more at the beginning of the training. So if there is high temperature and low temperature, that means your
More certain.
yes, so more certain, which means some neurons or some paths will totally get destroyed from the very early on. But this way, by retaining the temperature to be 1 over square root of d, they found that to be more stable from learning point of view. But beyond that, I'm just saying what I've read. I've not experimented myself.
So what is it that keeps like the sum of the logits in a good range? What about the loss function drives that?
I think that's what Julius is suggesting, that maybe there should be a learned parameter rather than a fixed parameter for the temperature over time. I don't know if learning that hyperparameter is going to be too much of compute overhead. So initially they tried with scaling by 1 over d, but that did not work that good. So then they tried with 1 over square root of d, and that seemed to have scaled much better for them from the variance containment point of view.
From the variance, but what is it?
And the learning as well, because then all neurons were, all paths were able to contribute.
And so are those typically just before the softmax then?
Yes, that is scaled after
Okay, so that's what keeps it in range. Yeah, okay.
Yeah.
So you still could.
X is self-normalizing. So if you go back to that formula for softmax, it doesn't matter what goes in, it's going to normalize it. But if what goes in is too hot, then it will be like the large gain example where there's a winner that takes all, perhaps unjustifiably. But if
well, this would be cold, wouldn't it? This would be cold. Winner takes all. Hot is going to be.
Yeah, because it divides by
right.
It divides by right.
Yeah.
Right.
There it is.
Yeah.
Yeah, it seems like it should be learned. And what I was speculating, when I gave my talk, was that maybe they really want to do power normalization here, because the attention sum is a sum of vectors, and the vectors, because there's RMS norms all over the place, the vectors tend to gravitate to the hypersphere, unit hypersphere. And so when you do an attention sum, then you go outside of that. And so if you divide it by the square root of the number of terms in the attention sum, that would be power normalization. So under the assumption that the vectors tend to be orthogonal, then that would be exactly the right normalization. You wouldn't even need an RMS norm. But in the square root of model dimension, that would only really match if the width of the attention sum was equal to the model dimension, which is not the case. But
Oh, I see what you're saying. So this should be the dimension of the head, attention head, not the dimension of the model. Is that right?
Yeah, that's right. Yeah, the attention head. So yeah, it's like the model dimension divided by the number of attention heads.
Yeah.
But what I'm saying is that it's what would really be power normalization if you divide it by the square root of the number of terms in the attention sum, which is the context buffer length, which is a much bigger number typically.
Oh.
So yeah,
I see.
Comparable. Yeah, so if your attention head dimension is comparable to your context buffer size, then you can say that you're doing power normalization of the attention sum based on the assumption of orthogonality, more or less, And that would be well behaved going into the softmax, because you've got this nice unit normalization going on, and then you
Right.
get the softmax and get a distribution that's normalized.
So we'll have to save that to the last 15 minutes because that's when we create the brainstorming list. And it sounds like that should be one of our experiments.
Yeah,
Yeah,
that's
interesting.
absolutely.
Okay.
And account for the lack of orthogonality, that you can, adjust the scaling between, dimension and square root of dimension based on how orthogonal or not it is.
Yeah.
So, okay.
Okay, so I want to try to wrap this up quickly. So I also did it when it's not this example up here, I had an exact match between a key and it's a repeated key, I think, in this sequence. Yeah, in here I created the same key 10 times in a series of random ones. And that's why you got these little matches at multiple locations, but one was at the offset that I was looking for. And that's why it highlighted the one that was at the offset I was looking for and dumbed down all the other ones. But I also wanted to say, well, so what does it look like if you don't get a match? There's not the right key at exactly the right position. Then you get this spread that's noisier. The threshold, the noise floor here is quite a bit noisier than the exact match. And then you get a lot of peaks. And when you run that through, it pushes the noise floor down and pulls up the matches, but you kind of still preserve this. It's not an exact match, and you get a bunch of partial matches. Okay, that was the end of my experiments with softmax. Any other questions on softmax? And then just a real quick, let's see, was there anything I got out of this? I wanted to understand subspaces because we had talked about like the position embedding subspace versus the semantic subspace, etc. And so I just created something that allows you to create orthogonal bases just by picking one and then picking another and subtracting it by all the dot product with all the other ones so that you make it orthogonal to the existing ones, and you end up with a basis, I guess normalizing it each time. And you end up with a basis that's n bases, but they're all orthogonal. Project into a subspace, take a vector, project it into it. Validate the subspace by just making sure that all of the orthogonal subspaces means that all the bases in one subspace are orthogonal to all the bases in another subspace. Validate that it's within a subspace, make sure that that a vector is projected into the subspace is the same as the space, so there's nothing outside of it. Anyhow, just played around with those and then testing superpositioning once I had orthogonal spaces. So the idea here is we conjectured that you would have subspaces that represented position, subspaces that represented semantics. And I just wanted to see how those worked. So if you were to do superposition within one subspace, the more elements that you add, you get more and more noise added, meaning that if I have, if I've added two vectors, I get superposition of those two vectors, and if I dot product them, I can kind of query for one or the other. But as I get more and more added in, the result is noisier. It's not exactly one. It can be a different match based on the interaction between the two queries, two vectors that are already been added together. And just confirm that if, in this case, I'm adding them, but there's one subspace for that I have several added, and one that I'm doing the query on, and they don't touch each other. So you get, you don't get noise when they're in separate subspaces, basically. Kind of obvious, I guess. Subspace that avoids the lower 200 dimensions. So I guess that's the same thing. I'm going to zoom past this because I don't think this is. Oh, here I was just defining subspaces that this would be semantic subspaces that don't use the lower dimensions. And what am I querying? Querying position 0 against the sequence. So if I have semantics that don't use the lower dimension, then my ability to kind of locate them, the attention, the pointiness of the attention, gets very smoothed out.
I wonder if anybody's looked at where things go in the space based on how much they need precise localization. You know what I mean? It's like the learning should just things that don't matter that much would gravitate to the high dimensions, and then anything that you need to know very sharply
Yeah.
would gravitate to the lower dimensional components.
Yeah, that's kind of semantic embeddings, learning what part of the subspace they want to occupy based on the types of queries that are going to be run against them.
Mm-hmm.
Yeah. I mean, this is just, I was just playing with the subspaces to see how they interact. I haven't looked at any of the embeddings, although that might be one of the things we can do in our VSLM project, is to look at, I don't know if words would be that way, but yeah, it might be interesting to see if you have RoPE as your position embedding, if some end up finding vectors up in the high dimensions and others are centered someplace else. That could be really interesting. Okay, I think that was it. So that was my playground, and I'll post that in case anybody wants to look at it.
You naturally write nice unit tests as you go. So after your presentation, I really believe that the code is right.
Oh, it was fun. It was fun just playing. I think you get a lot more out of it writing it than talking about it, but or watching somebody else talk about it. But it was interesting anyhow going through. Okay, so that's the first third. The next thing was, and I'm gonna zoom through the next so that we make sure we have time for the project talk at the end. Okay. Let's see, where was this? I think it was this one. Oh, no, that's the, yeah, okay. Attention with linear biases. So this paper was, I originally kind of brushed off because I hadn't really heard of these linear attentions as catching on. So while it seemed like a good idea, it seemed like if it's not getting the quote unquote attention, then maybe it isn't that great of a thing. But it was interesting as I read through, partly because of some of learned a little bit more about the other approaches. So attention with linear biases, basically, they do the thing where instead of adding they're not like the original attention is all you need, where the position is added to the original token, added to the residual stream. It is also one where they add it to the query. And basically what they did is they would run the dot product to get the logits, and then they'd basically just add a bias to the logic. And the bias would be favor more recent matches and disadvantage matches that are further away. So it has a kind of a nearness bias towards it. And what they did is, and I think they had a picture that was pretty simple that captured that. So you take your key and your query and your key, and you get this masked attention matrix. So this is all the logits basically. And then they add this lower triangle matrix times some sort of scale. And that scale then moves those points up or down based on how close they are. And then when you run it through the softmax, it's going to be more inclined to pick a match that's close. So if you had those ones like that last example where I had lots of matches, it would have, it emphasized this because this gets some value added to it. Or I guess were they showing it as negative values? Negative, so a lesser negative value added to it. So it pushes down the ones that are farther away, leaving the ones that are closer biased. And that's all it is. And the one other element is that M is a head-specific scalar, so each head has a different bias, kind of a different slope to that line. My intuition means that some heads are going to be more effective close in. Some heads are going to have a longer range because they don't bias the farther ones as negatively. So they have kind of a longer range reach. But that term is head specific, and it's not learned through training. They just picked them. And yeah, and that's kind of all this is. They contrasted it with T5. I had Ted's not here, is he? I had a little bit different read. I thought Ted had said something where one was added before the softmax, one after. But to me, it looks like they're all added before the softmax. And the difference between this and in the paper when they were talking about RoPE, they talked about the relative position not being computationally advantageous, or it was computationally disadvantaged. This thing right here, I think, was one of the ones I referenced in the talk, where the T5 bias was the speeds were much lower. I couldn't quite understand why that would be, except that in the case of T5, it looks like T5 learns a bias based on position to be added. So it's the same thing as this guy, but instead of being just constants with a scalar that we pick, it was learning the values that you had to add into here. And so you end up with more parameters to learn, and you end up with larger, well, I guess it's just a larger parameter space that you have to learn. But computationally, it seemed like it should be the same thing, because they were just taking these learned biases and applying them to the thing. Whereas in this linear bias, it's just a constant that they use. So that was kind of interesting. I also searched around. Let me just scroll through here and just see if there's any other highlights I wanted to pull up.
Hey, Roger, so
yeah.
So that was the training speed. How was the inference speed comparison?
Yeah, that they talked about training is slower, but they also talked about inference is slower. And
which I don't understand. Yeah.
I might have the wrong understanding of what T5 does. I tried to look around and get that, but yeah, I don't understand why it would be different, because it's it seems like it's just a bias that's added.
And rotary is RoPE?
Rotary is what?
RoPE?
Yeah, RoPE, should have been RoPE, yep.
Okay.
This one was apparently came out around the same time as they were playing with all that.
I don't know if this is right, but I vaguely recall that T5 adds a bias diagonal, subdiagonal matrix or lower triangular matrix to the attention matrix. Is that possible? The whole attention matrix, like the QV cache matrix, whereas in Alibi, it's just adding it to the output of the softmax. So it's, it follows the attention calculation, or at least follows the score. It's actually after the dot product, I believe. So
for which one?
For Alibi, I think
Alibi is after from what I could read, Alibi is after the dot product before the softmax.
Okay, perfect. And
but
then
T5 would also be, wouldn't it?
I think T5 might be before the dot product. It might be, to the tension matrix. But as I said, that's a vague memory. I'm looking for the paper.
Oh, okay. So like maybe add it to the key values before the dot product.
That's my vague memory. Yes.
That would explain, if that's true, then Julius, that would explain that chart much more clearly. Because otherwise, Alibi and T5 should have been this similar performance, I would have thought. So what you're saying makes more sense with that.
Yeah, and it has to be recomputed every shift.
Right.
Which is more, yeah. Mm-hmm.
Okay, that makes a lot more sense then. I don't know why they did that, but
made sense at the time.
Yeah, I guess so. Yeah, so The other thing I was interested in is which languages. So there actually were, I don't know if I still have it here. I was looking for, no, I might have closed that one. There was Bloom was using Alibi. MPT, I don't know that one, but MPT was also using Alibi. So there were a few that were actually using Alibi. Not that one.
Wonder if there might be a patent on it. You always have to watch out.
Yeah, okay. I had one that showed where they were, but there are a few of the larger languages, at least language models that I recognize the name of, that were using it. So it's not a zero, but it's, and I don't know, does anybody know? I was assuming that RoPE was like the winner, but I'm not sure that that's true. RoPE does have the advantage, it seems like, that you can have, you know, a fairly accurate positioning. Like we saw that attention, you know, a very sharp attention to a specific time. It's added as you go. And actually, if it's also present in the value, again, you might be able to kind of recall two different keys or two different values and do something with the distance between the two of them. So it seems like it has that advantage. Okay, so let's see, is there anything else in here? The original paper tried adding learned as well as sinusoid, but he liked sinusoid. This is where we talked about the rotary. We already did that. Here's the T5 one. Compute the attention values before. See, it says we compute the attention values as before, but then we add a learned shared bias to each query key score. So Julius, this sounds like it's the same.
Oh, you found it? I was looking.
Yeah, here, this is in the Alibi paper discussion about T5 bias.
Okay.
So I don't know, I'm a little uncertain about that. And again, T5 does it, integrates at each layer at the query key. Okay.
Yeah, they said that theirs is before the attention calculation.
Who did?
Where you were showing, yeah, the very first sentence, it said.
No, maybe I read it wrong.
So the
And
first
especially
highlighted
as before, we compute them the same way. So the dot product's the same, but then we add a shared bias to each query key score.
is a score. So
that's, I take that as the score is before the softmax.
but is it before the query key product?
Well, that's what I thought this was saying. Compute the attention values.
Okay.
And that's what a query key score is, the attention values.
Okay. T5 bias method modifies the way the attention values are computed. Okay. Well, I'll keep a side thread on this and
yeah, there might be, I might have a misunderstanding, but there was something that was making that they claim T5 was slower.
Yeah, I found the T5 paper. I'm scanning it.
I see a bunch of chats going on. Is there anything in there that people, has anybody got any insight there that I'm missing?
I just had this image in my mind of the diagram. It was like a QV, it was like an attention matrix
for T5
bias that had negative. It was most negative in the lower left corner, and it was 0 along the diagonal, and you just added that. That's just what my memory has in it.
Well, that's what this is for Alibi. Here's your attention bias. It's a linear.
But it's only adding to the output. So it's the actual dot product itself that gets biased, not what goes
right.
into. Okay.
Not what goes into it. Yeah.
Right. So
there might be a different picture if if there's the T5 is different where it somehow adds it to the keys or something like that before doing the dot product, then that would explain the difference in performance. I'm not sure why you'd do it that way, but that could explain it.
Yeah, I'll try to find it in the T5 paper.
Okay. Anyhow, and I think that was all that I wanted to show out here. And then the other paper was this positional interpolation, which was interesting because when you're dealing with the position embedding and you want to go to the longer sequences, if you start using parts of this rope that are extended out beyond anything they used before, it runs into problems. It doesn't work out at that dimensions. And I think that it's, if we went back to this, oh, never mind. It's like those start touching into dimensions that haven't been used before, that maybe are used for semantics instead of position by the model. But if we instead change how frequently we sample these, much like Mamba, where you had, what were those polynomials? Does anybody remember? Dave, do you remember those that Mamba uses?
Legendre polynomial.
Legendre, that's right, Legendre polynomials. And they could change their window simply by resampling the Legendre polynomials. And this kind of sounds like the same thing. What we're able to do is extend our context window by resampling those sines and cosines at a finer granularity. So we're still using the same dimensions, but we're just sampling them more quickly. I don't know, maybe you could imagine that the shifts on the lower dimensions aren't far enough. You could maybe get collision between the vocabularies if they're not shifting enough. I don't know, maybe that doesn't work at some point. See ya, Dave, Sally, I mean. I always have a hard time because it says Dave when I look at the picture. Okay, so anyhow, that's what they do. And they find that they can easily, if they resample, and here's the equation that does the resample, I think. Yeah, it's right here. So they just, instead of using the position, M, they scale M by this original, the original length divided by the new length, the larger context window. And that strategy then allows it to be retrained. So essentially, they change the scaling, they start feeding the data through. Obviously, all the queries and everything have learned a particular bias to their, like how far back to look. Those are off a bit. But what they find is they can retrain the network just with some fine tuning after changing the scaling on the RoPE. They can retrain it in, I think they said, a few thousand to a few 100,000 examples. And it didn't really matter what examples they used, they said. Yeah. Fine tuning for 100 steps on pile.
Thousands.
Question?
You said 100, but I think it read.
I think
Yeah,
Dave said it was
1,000
1,000.
steps. Yeah, there was someplace else where they used that term, but yeah. A small amount, relatively small amount. Okay, so I think this is super cool. I'd love to see how many of the models right now have done this type of train on a small window and extend it out to a larger window using this approach. But on the other hand, there's not a lot to talk about. That's how they extend the context window, resample the sine waves at a higher frequency, do some fine tuning, and now you get this extrapolation where something that's trained on 2048 will work fine with 4096. And I think they went out to like 32K or something like that. This was probably the first example, but I think they found that they could extend it more than just doubling it. And and by the way, you could use an existing model. When you came up with a strategy, if you just happen to have a model that had been trained on 2048 and you'd spent, $15 million training it. This small change, you could now make it work for, 4K or a 32K context window without retraining it, which is pretty cool. Okay, any questions on that? One thing I might mention too is that in Alibi, no, it wasn't Alibi, it was T5, I think it was, what I was reading, where they actually, the learned bias that they had wasn't linear. So they said that it worked well for like position attention was important for short ranges, but less important for longer ranges. So they kind of made it so that out to a certain range, they had some resolution. Anything over a certain distance in the sequence, it was all the same. It just didn't matter. Julius, did you find something cool? Can you summarize? Do my chat GPT?
Yeah, but I'm not sure I understand it. It says, since self-attention is order independent, it's common to provide an explicit position signal to the transformer. So we all know what that means. While the original transformer used a sinusoidal position signal or learned positional embedding, it's recently become more common to use relative position embeddings. So it looks like they're moving from, absolute to relative. And so they say, instead of using a fixed embedding for each position, relative position embeddings produce different learned embeddings according to the offset between the key and query being compared. Okay, so that's just relative position, no problem. So here's what they say. We use a simplified form of position embeddings where each embedding is simply a scalar that is added to the corresponding logit used for computing the attention weights. And I'm not sure what that means because I think of the logits as the output of the softmax and the attention weights are the output of the logit. So I'm
yeah, it seems backwards, right?
Okay. Yeah. What does that sentence mean? That one sentence. So the embedding is a scalar, which is like Alibi, negative bias. So the farther away it is, the farther the distance between query and key, the more negative the bias. So I think they agree on that. But they say that they're adding it to the corresponding logic for computing the attention weights. Do they really mean dot product? Because then it would be the same.
That must be the scores, yeah.
Yeah, that would be the same, but it would be, yeah, the attention weight would be the final score, wouldn't it? It would be the output of
the term needs definition, but that's what I'd guess it is, yeah.
Yeah. Yeah, it looks like it's the same thing.
The one thing that advantage it seems like for the T5 is that it seems like each head could learn like a different distance, whereas in Alibi they're hard coded. The choice was made ahead of time. Although they did some ablations, but it was fixed. Okay. Any questions? Last 1 minute of RoPE. Anybody?
We're at the end of our RoPE.
We're at the end of our RoPE. Thank you. That was good.
Roger, I saw some where, are you going to share your notebook that you have?
Yeah, absolutely. I'll post it on Slack.
Okay.
I'll post it on Slack under general.
All right, thank you.
And I also will post it right here, right now. Okay.
If you want to drop the slides too, that'd be super great.
Yeah, I think we need a better way to keep track of those. Oh, I just did drop the slides. Sorry.
Oh, okay.
That was
That
the
works.
slides. That was the slides. And there's the notebook. And let me know if it should have permission to see that as long as you got the link. I think on both those. Okay.
Well, Roger, before we get off that, can you put those somewhere else so we can put them into the YouTube thing too?
Yeah.
Okay.
Thanks. Okay. So let me do, Herlin, I'll follow up on that afterwards then. Let's see, actually for the notebook,
Yeah, it looks like the permissions on the collab are restricted.
Try
More.
again. Try again.
Try again. Let's see. I got it. Cool. We're good. Thank you.
Okay. Okay. So now moving on to VSLM. So in absence of having a meeting last week, like I said, we got together and we were just brainstorming a little, talking about some of the ideas that have been thrown out, and this idea of following the CarPath, the Nano GPT. I was kind of excited that this idea that we could actually have a model that was small, small enough that you could actually, with your hardware or borrowed hardware, Dave, you could actually train a model and have it do something. And I guess if you look at Nano GPT, there's a simple one, super simple one that is character-based tokenization, and you can train it on a CPU in like a couple minutes and start to talk Shakespearean, which is pretty cool. And so as we were talking, there was a bunch of ideas that came out about things that would be interesting to try. Julius, you just had this, scaling of the output or the input to the softmax, I guess it was. Little ideas like that, like how would this change things? And so we came up with this idea of, wouldn't it be fun to have a project that was just long running, in the background, accessible versions of the language models that we could play with on our own equipment or in the cloud, or Richard's not here, but he's volunteered in the past to lend a little GPU time. And wouldn't that be a lot of fun to explore? So we put together this idea of this VSLM and a few things that are created from that. So first of all, there is a GitHub repository that I created for that. Right now it's just empty, but it's a place for us to put that. The idea would be that we clone it and just get the Nano GPT running. Ted had suggested using tiny stories as a data set. It's pretty clean. It's pretty small and easy to use. So there's that. And then start looking for what's a model size that we can train. It doesn't need to be 2 minutes on a CPU, but a couple hours on a GPU would be nice. That makes it accessible. We can run multiple experiments, et cetera. And then one of the things I'd like to see is, what does that mean? Like, are there benchmarks that are dumb enough that we could actually see our performance from a benchmark? It's kind of cool that you can estimate the performance of your model by just looking at the loss function. And I'm not entirely sure I know how this is related, but the perplexity and loss function both kind of have that slope down, and you continue to train it, and the loss function gets lower and lower, meaning that when the task is next token prediction, it means that over time it gets better and better on average at predicting what the next token in the sequence is going to be. And that makes it pretty easy for us to see how are our changes affecting the model. I hope. So that was the project. Does anybody have, I didn't get a link to, I should have got a link to the CarPath, the Nano GPT video. Should have got that to include. Let's see here, this is, okay. Yeah, I don't have that.
Let me go look for it and I'll post it.
Okay, but that's a good one as kind of a baseline. The places that for us is that started this GitHub for everybody to contribute in. There's a sub project on this. I think this should mean if you check out VSLM, you'll get a copy of the sub project. I think I just need to, I haven't published it yet. That's probably why. So that there'll be a Nano GPT repository underneath this in the tree. And we can use that for doing our modifications, et cetera. So it's kind of a separate repository, but it's also part of the VSLM. Assuming that we're going to start with Nano GPT, I could see us also outgrowing it. We may want to get to where we use like Hugging Face implementation or something like that. later on, but NanoGPT is a great place to get started. Okay, that's great. So we'll, in the meeting notes, there's a link to the video. I'll add that to the repository, or maybe Dave can. I also.
Hi, everyone. So by now you have probably heard of ChatGPT. It has taken the world and the AI community by storm.
Somebody's got it.
Oh, sorry, that was an accident.
That's okay. That's okay.
I didn't even know it was me. Terrible.
So I also added VSLM as a channel on our Slack. So if you're interested in it, we can kind of post things there for just discussion about ideas, etc. And then part of the repository, where did the repository go? Oh, here is the repository for Karpathy's posting of NanoGPT. And it's really fascinating seeing him walk through kind of the evolution of this thing. But it's basically this simple. There's a train that you run, and there's a sample that you run. And the train uses configuration files, which is basically a way of, so like train Shakespeare, it's basically a way of setting the parameters. He uses the configuration to kind of set parameters. So things like the size of the GPT, you know, how many layers, how many heads embedded inside, etc. He does have it linked into WANDB, which is nice for tracking progress. Various things like, you know, how often do you evaluate it, your constants like learning rate, types of things. These are all learning rate issues, beta. So those guys at the beginning, oops, what did I do? Oh, one more. So he sets up some defaults first of all, and then this is his way of, where do you do this? This is his way of overriding some of the defaults. He does use compiling, which I haven't used before. This seemed to have watch his video, but this had a significant performance gain on it. One thing I will mention is he uses bfloat 16 if CUDA is available. This makes an assumption about, I forget the NVIDIA architecture that supports B16, but if you go on Colab, some of their T4, is it T4? That GPUs do not support the B16, so you have to change that to be just float 16. He also has it set up using Torch Configurator, I think it's, no, Torch. Simple install, minimal dependencies. This is how you run a GPU one. And it generates this type of stuff after a very short amount of time. It sounds Shakespearean, but it makes no sense. But and then he also goes all the way through GPT. I saw a few different references on this. Let's see, to reproduce GPT-2, 124 meg, you need 8 A100s, and it runs for 4 days. So that's a little outside of scope that I was thinking for us. But he does have it set up so it'll run with DDP, which is basically a way this torch run starts up a number of processes, and they communicate. There's one master and multiple slaves, I guess, and they work together in it. And that apparently it'll work on a cluster. Oh yeah, down here, it'll work on a cluster as well as multiple GPUs in a single machine. So that's all embedded in his little, what is it, 300 line train.py. He's got some, he validated it against GPT-2 weights that he got from Hugging Face, I think. And he did some fine tuning on it. So it's got kind of everything, the sampling, everything there. And let me get back to jumping through training. There's not a lot in here. There's the DDP stuff he was setting up where he'll start multiple ones. He can also What's this stuff? Some CUDA stuff on the master. He has his own data loader thing that he uses, so he's not dependent on the X. I don't know how critical this is. It's fairly accessible this way, but like I said, we may want to at some point switch over and use like a Hugging Face model where some of that data loaders and things like that are already predefined. But this is a good kind of starting point. He goes through and yeah, this generates a vocabulary size just by looking. So if it exists, he uses it. What happens if he doesn't? If it doesn't exist? I don't know what he does if it doesn't exist. Okay, then if you're training from scratch, it does this. Otherwise, it'll load some prior saved model. So he has checkpointing built in logic where later on we'll see where it saves them. And this is the one where he did a good kind of baseline check. He ran it against the weights from Hugging Face. This, not sure what that does. He talked about block size needing to be a magic size. I don't know if that's what that's doing. Compiles the model. The estimate loss just runs against the validation. Also train just to see what the loss is averaged over that range. Learning rate, he implements a, I think a sine, yeah, implements a cosine learning rate. So it goes up to a certain level and then cosine down to a minimal level and then stays there. He's got 1dB integration. Here's the loop going through the training data, get the learning rate. This is where you evaluate it. This is where you go through. So microstep is basically, here's where you're running the model forward to generate the logits and the loss. And then you're doing your backwards propagation of the gradients. In microstep, actually that's not the accumulation. Backwards path gradient scaling if trained in FB. So that's gradient scaling is something else. I'm not quite sure what gradient scaling is. But after some microsteps where you've accumulated the loss, then it's you will do for that micro batch, you will apply the gradient using the accumulated gradients from multiple micro batches. And that's pretty much it. Here's some reporting, I think, goes on here. And that's the whole training program. So 336 lines and you get a full standalone language training. If you follow his examples, they were pretty straightforward. It worked. So that was cool. And we could go through it we can kind of talk about what we want to do, how many people are interested and how detailed we want to get. We could do a code walkthrough or something like that in a launch meeting someplace later. So the one other thing I wanted to point out was this page. Which is just a Google Doc for us to put ideas about things that we want to train. So we'll put on here, what do we call this? Power scaling? Power scaling of, is that, Julius, power scaling of what do I call that? Is that of the logits?
Power scaling of the sum. So the attention sum.
Attention window, or
it's the attention sum.
values.
So, yeah. So you're adding together a bunch of vectors with a dot product score, and if they were all correlated, then the softmax would probably be a pretty good normalization. But if they're not correlated, then really they add on a power basis, and so what you really want to do is divide them by the square root of the number of terms in the sum, not some dimension.
Gotcha.
Just how many things are you adding? It's just like panning in audio. if the signals are uncorrelated, you do square root law, sine cosine panning, whereas if they're correlated, it's linear panning. Same thing, you're just sort of adding things in a normalized way. And normalization's different for uncorrelated and correlated signals. And a vector is a signal. I mean, that's, you can think of them as exactly equivalent.
Yeah. Okay, so this document I just thought would be eventually I'll take this and post it into the GitHub, but I thought it'd be easier for people to drop things in if it's a shared Google Doc. These were some ideas that we had discussed, and I just written them down, so I'm looking for more inputs into it. But Ted had this experiment he wanted to do where the idea is that when the model learns context learning, you actually find that if you plot the average loss by position in the sequence, the loss should decrease over time. And when you see that, that's kind of the definition of context learning. You're able to use earlier information in the sequence to make better predictions later in the sequence. There's some experiments that I was thinking in terms of the residual stream. Why is it the residual stream starts with the last input token? And could you instead start from some learned most optimal starting point for sequences or for token prediction? Experimenting with different sizes of layers. Why is it that all the layers have exactly the same size? The model dimension is the same. The context window is the same. The size of the MLP and the QV are all the same. And why is that? And I have kind of an intuition that would say that the earlier layers would probably be kind of formulating complex embedding from the tokens. If you need to put Eiffel and Tower together, that type of thing would be happening early on in the early layers. Somewhere around there's kind of some sort of embedding that captures the sentence. And then in the middle, and so those are fairly small embedding dimensions and also fairly short context windows. In the middle, I'd be thinking of larger semantic things and a lot of context. So it seems like longer context windows, larger embeddings so that you have you can do more superposition. And then at the end, if it's getting down to where, okay, now I know the sentence what I want to predict, and the last few layers are figuring out where am I in that sentence and how do I compose that sentence type of thing. No science behind that, just kind of a gut of, gosh, it seems like it should work like this type of thing. So I'm kind of interested in, and Ted actually had some similar things, similar experiments along the same line, where he was thinking of it more from the context of, instead of the residual stream going all up the whole way, how about if we just gave the model some space that doesn't go all the way up to the next token predicted, but is just kind of a workspace that I can put things in and use that to aid in predicting the next token. So a bunch of things associated with that. Another one, weight sharing, is the way I captured it is, I've wondered about how deep these networks need to be. And is there something, and how different are they at the different levels? Or could you think of it as more of a recursion within the layers where maybe you do with a given state, you do certain processing that gets you to another state, and you could actually maybe use all those same weights again with a new state and propagate back up again and do that, and then have some sort of I'm done looping type of signal coming out of it. So that's what I was calling weight sharing. I saw some difference in, I did tiny stories and I did IMDb by accident and saw a big difference in the learning curve. I think they call it the horizon of optimal compute or something like that, where these language models come down to this line, and no matter what, it's hard to get past that line. It's one of the things I think is in the scaling law papers, which would be a good paper to cover. But I'd like to see how that changes with different data sets, because I think when they did the scaling laws, they had they sampled different sizes, subsets of the same database or same data set. So it'd be interesting to see, what if we change the data sets? Are these different data sets, are you able to actually learn, get a lower loss with some data sets than others? There's another one. Another area that's interesting to me was this separation of reason and knowledge. A lot of the big models, it's like all of the information that's out there has been crammed into these weights. Whereas to me, it seems like that's not necessarily the best way to store the knowledge. What I would like to have is a smaller model that knew how to reason given the data, and have the knowledge somehow stored elsewhere more effectively and kind of easily switched in, kind of like RAG, but RAG starting with a model that knows the minimum amount it needs to, and can do as much as possible in the augmentation and as little as possible in the model itself. That was another one. One of the guys, Grant, what was Grant's last name, Jerry?
I don't
Anyhow,
remember. I can look it up. Yeah.
Grant had this idea. He was looking, did kind of a from basics look at optimization, SGD, and his intuition was there was a different way to do, instead of gradient descent where you jump kind of horizontally at a fixed distance, what he was wanting to do is move along the curve at a fixed distance. So he called it tangent descent. We called it Grant descent, but he wanted to come back and call it tangent descent. But just a different optimization strategy. I've tested it on a real simple thing. He's tested on a simple thing, and it is much, much less sensitive to learning rate. And so it might be interesting to try it here and just see if you could crank up the learning rate and have it automatically adapt. One of the things that is kind of easy to miss is that Atom, which is the go-to optimizer, it uses up like 3 times the model size in all the parameters that it stores. It's a huge memory hog. So if you could come up with something that could do model training without Atom, but still be efficient and robust, that'd be kind of cool. So that was that one. That was the first set of ones that I remembered from our discussions, and I jotted down. But looking for people, if you have things to explore that you want to explore, let's just get them down on paper. And for people that are interested in actually running the experiments, we can do that. Like I said, I started the repository for us to play with. I have, I think it's back here. Yeah. I have started playing with a fork of NanoGPT, and I will add that sub-project into our Git repository. And then what we can do is just I'll try to create a baseline that we can work with, and then people can just branch off their own personal one, and keep it all in one repository and make it easy to share little pieces back and forth if you want to run experiments. So that was the pitch. It'd be nice to get a sense of the level of interest from people. Ted's not here. He was excited about it.
I've got my clone already.
Yeah, I'm interested in doing it. My concern is just how much compute resources do we need to make this run,
So Dave has been kind enough to let me borrow his compute. And so I've been running some experiments, and I don't know if I don't think I have anything I can show, but it gets to where you can get stuff out of it.
Do you know what the time is just to recreate the Nano GPT thing?
Just to run their Shakespeare is just minutes.
Oh, okay.
Shakespeare is easy. There's other ones. I'm trying to see if I have any samples. I think I cleaned things out. Oh, here we go. I did keep some samples.
That was for tiny stories on that, right? So for a big database, it was 4 days.
No, well, that's if you wanted to train a model equivalent of GPT-2.
Yeah.
But so what I did is I have, can you see that?
Yes.
Okay. So I created, this is my Nano GPT subdirectory under the VSLM, sub-project, whatever they call it. And I defined a tiny stories. So it reads from tiny stories, but it uses character embedding, character level tokenization. And the model, I tried to pick something that was kind of halfway between here's Shakespeare, which is 66384. So, and if you look at GPT-2, it's, where is his heads? Oh, okay, I don't know why it's not there. Oh, they're just comments up at the top. Okay. GPT-2 was 12.12.768. And so I just went with an 8.8.576 as a model. So it's kind of halfway. I don't know what that works out to. Is it the square root of the number of parameters, or, but the dimensions are kind of halfway in between the two. And that's what I created and started training. And it's if you start out with so this is a model that's doing character level prediction untrained. So it's a random network. So the prompt is, this is a story about, and it's just predicting gobbledygook, as you would expect. This is within 1,000 iterations. It's already learned words. And I forget how long this was, but I think this is like 5 minutes on Dave's machine. He's got a super hot machine, but
I'm just wondering, what are we going to have to purchase here from, GPU time, things like that?
I think you would be able to do this pretty easily on Colab, for instance.
Okay.
You have to make a change so you're not using bfloat.
Yeah, that thing you mentioned before about the VFloat.
Yeah, Dave's got 4096, right, Dave?
I think
yes, 40. Yeah.
Yeah, and so it supports the bfloat 16.
4090, yeah.
What does the B stand for in B float?
I don't know. There's a picture, there's a good graphic that shows what it is, but basically they expanded compared to compared to float 16. Float 16 versus float 32, they reduced, I think, both the mantissa and, is it mantissa and exponent? But in the B float, they shifted it so you have more exponent and less the mantissa. So it's like less precise, but it has a wider range.
Nice. Yeah, that makes sense.
Yeah.
Yeah, there's a Wikipedia page on it I just found.
Oh, okay. So here, by the end of this 9,000 training, this is a story about, this is a story about octopuses and most beautiful fish. So it's knowing some things fit together. One day the kids came to the park and saw a big tree. This is a story about a prince and a dragon. It makes them feel better. So it's not literary yet, but it is starting to get some association of words that kind of make sense to go together. I think, I don't know. There's another one
So are you using NanoGPT as a sub-project? Because I did a pull on VSLM and I don't have that.
I think I haven't pushed it yet.
Oh, okay.
I'll push that change, and then I've been just scratching in it, but I'll commit those and push them so that we got it. And then just like I said, what we can do is we'll try to create a kind of a main branch. I don't know if it should be main for GPT part, but something that's our VSLM branch, which will be our quote unquote main, not related to the Nano GPT main. And then we can each individual have branches off of that.
Yeah.
So, and if you want to contribute, just let me know and we'll get you added as a contributor. Otherwise, you can just use pull requests to get stuff in.
Mm-hmm.
If you want, just fork it off. Anyhow, I'm way over, so let me stop there. That was just kind of the launch and the invite to think about the type of experiments that you'd like to run and drop those into that page. And then we can decide, depending on how many people are interested in what level, we can decide where we want to have conversations and discussions about the types of experiments to run. That makes sense?
And so
Okay, I'm gonna stop the
use
recording.
Collab, right?
I use Colab, but for here I was just using VS Code.
Okay.
Yeah.
So,
But on
And then
Dave's
depending what-
machine, right?
Pardon me?
On Dave's machine.
Dave let me borrow. What we could do though is we can get it. I've used in the past, used just the Google Compute Engine is an easy way if you don't have your own to launch those, and you can get them for, the T4, I think it's called. You can get that for less than $1 an hour. So if you got a couple hour experiments, it's a couple bucks.
Mhm.